In this video, we're going to derive the pullback or vector Jacobian product rule for matrix-matrix multiplication. For this video, we want to think of matrix-matrix multiplication as a function that takes two matrices. Let those be rectangular matrices, the first one being m by n dimensional and the second one being n by o dimensional. And then we perform the matrix-matrix multiplication, contracting the innermost dimension, and as a consequence, the resulting matrix C shall be an m by o dimensional matrix. For the pullback or the vector Jacobian product rule, we have the task to backpropagate cotangent information on the output, which is given as C matrix with a bar denoting the cotangent here, and this shall be a matrix of the same dimensionality as the output matrix, so it is another m by o dimensional matrix, to the inputs, and those are matrix A bar of the dimensionality m by n, as well as the matrix B bar with the dimensionality n by o. And this particular pullback or vector Jacobian product rule is quite important, as you find this in the backpropagation of neural networks, so the backpropagation of neural networks, so in an application for deep learning, for batched inputs. So you not just look at one particular sample, but a bunch of them and compute them through the neural network. And now you want to obtain a gradient estimate. And so this particular rule we're going to derive here will play a big part in that. Informally, we can think of a pullback rule in a sense that we will take the Jacobian of our function. So this will be df by an input, and let's say for instance a. So we will derive the matrix-matrix multiplication with respect to a, and then we will left multiply that with the cotangent of the output, which will be c bar, and then we have to do some kind of a contraction, because if we derive a function that computes a matrix with respect to a matrix input, we would get something like a rank 4 tensor, and then we want to contract this from the left with the cotangent information, and typical symbolic notation would be used, the colon here in the double contraction. So we will contract the cotangent information with the numerator in that sense, and this will then give us the cotangent information on the input. And we will have something similar for the cotangent on B, where we will have the cotangent on C double contracted with the derivative, but this time with respect to B. We have to be a little bit loosely here, because this is no longer a Jacobian in that sense. It's a rank 4 tensor, but we can still kind of think of it as a vector Jacobian product, as something left multiplied with this derivative object. And it really makes sense if we start looking at index notation. So let's go into index notation to remove the ambiguity of symbolic notation. And for this, I first want to write down the forward computation again. And the forward computation is the original primal computation, in that we know that C, matrix C, and let's give it some indices, let's say index ik. So the resulting matrix C indexed at the ith row and the kth column will be given as A, ij, multiplied with bjk, and here we will use the Einstein summation convention. So if there is an index that appears twice, so in that case the j, we will sum over that. So that is the Einstein summation convention, and in a sense this is what our matrix-matrix multiplication is doing. It takes the innermost dimensions and contracts them. Okay, then let's express the pullback also in index notation. And here we have two different pullbacks, one for the first input A and one for the second input B. So we will have A, and let's also give that some indices, let's say mn, and give it a bar here. And this one will be given as C bar ik multiplied with the derivative of Cik with respect to Amn. And here I replaced f as the function with its output. So the function we have here is only computing one output, so the matrix C. So taking the Jacobian of the function with respect to the input is kind of equivalent as taking the derivative of the output with respect to the input. So this is equivalent to a df by damn. And we will have something similar for our B. Let's do B bar, and let's also use the indices bmn. and then this will be C bar ik multiplied with the derivative of Cik with respect to Bmn. And here again, I want to highlight this double contraction. So here we have in our forward computation just a contraction over the j, but in this pullback we have a contraction over both I and k. And this is what in symbolic notation we would have as the colon. But I think it is more precise if we write that down here in index notation. To now evaluate the pullback, we have to evaluate these two derivatives. So let me indicate them. We will do this one first, and then afterwards we will evaluate this derivative. And in order to find that, we will look at the forward computation and just perform the derivative and then plug it back in, and then we find a closed form solution for the pullback. So let's do that one first, where we will take the derivative of Cik with respect to Amn. So let's go at the forward computation, and we see we want to derive this expression with respect to Amn. And then we see that the matrix B does not depend on A, so we do not have to do any product rule here, and can just propagate the derivative operator and get dAij with respect to dAmn, and then multiply it with bjk. Okay, then we can evaluate this derivative, and here we are deriving a quantity with respect to itself, and it's not just any quantity, it's a matrix here. And if we derive a matrix with respect to itself, we would get like a rank 4 tensor, but this would have a particular structure. It has kind of only ones on the main diagonal, because it would only be 1 if the indices match identically, and otherwise it would be 0. And we can express this by the help of Kronecker deltas and say delta Im multiplied with delta Jn times bjk. And so the result of those would be 2 multiplied Kronecker deltas. And let's go to the second one, which will be the derivative of Zik with respect to Bmn. And here also the derivative operator propagates. So we will have first Aij and then multiply this with the derivative of bjk with respect to Bmn. Same idea, let's use the Kronecker deltas. So the Aij stays, and then we will have delta Jm and delta Kn. Okay, then we can use these two to plug them back into the pullback, and then we will first have the pullback for the A input. So A bar to indicate the cotangent, index Mn is C bar index Ik, and then plug all of this in, which will be delta Im, delta Jn, bjk. Okay, then let's apply the property of the Kronecker delta that induce an index change. We have the option to go from index I to M or from index M to I. Here it makes sense to go from index I to M, because this then matches the left-hand side of our computation. So let's change all indices in that multiplication that have an I to an M. So we will have C bar mk. Here is no I involved. Then let's also apply this Kronecker delta and change from j to n. So we have a j here, so we will get bnk. Okay, let's leave that for a second. We will come back to that and evaluate the second pullback, so which will be b cotangent index mn is c cotangent index ik multiplied with aij. So I'm just copying this result here, multiplied with delta jm, then delta kn. And let's change the indices, go from j to m. So we will have c, or let's go here first. So let's say aij, and j goes to m, so aim, and then k to n, and have here the index in. Okay, now we have the pullback in an index notation, but I want to have this more intuitively back into symbolic notation. So let's denote that and say we go back to symbolic notation. And in order to do that, we have to identify certain basic operations in symbolic notation, and that would be a matrix multiplication in our case. So let's look at that one here first and see we have the cotangent matrix C is somehow matrix multiplied with B, but not with B itself, but rather with B transpose. Because we see if the innermost dimension have to match as we would have it in our primal computation, we have to transpose B first. So we kind of have a matrix multiplications with the columns of B instead of the rows of B. So we will do the transpose. And as such, we will get that matrix A cotangent is given as C matrix multiplied with B transpose. And something similar holds true here. The cotangent on B will be given as, okay, so here we also have to match the innermost dimensions. So we could, for instance, transpose C, and then we would have C transpose would be having the indices Ni, and then the innermost which match again. But here we have to be careful. The result of that computation would be a tensor with the indices Nm, which is exactly the transpose of the B here. So rather, what we would have to do is A transpose C cotangent, because then we would move that over and say that is equivalent to saying Imn and Cin, and then we only need the transpose on the I in order to get the matching indices on the resulting tensor, and the innermost indices, in our case I, would contract. And then finally we can write down the full pullback rule for the matrix multiplication, which is what you would implement in your automatic differentiation engine. So the pullback on the function f, which we associated as the matrix multiplication, takes the primal inputs a and b, as well as a cotangent input on the output c, and then it computes first the primal output a times b, so this will be our matrix C, as well as cotangents on both of the inputs, and we will get the cotangent on A by doing C times B transpose, and we will get our, or let's first write it down, that's the cotangent on A, and we will get the cotangent on B by doing A transpose C cotangent, and this is the cotangent on B. And this is the final pullback rule, what you would, for instance, use in the backpropagation of batched neural network evaluations. A big thanks to all the patrons of the channel. If you also want to support my vision of free education on these advanced mathematical topics, you will find the link to the Patreon page down in the video description. I hope you enjoyed that video. If you did, then please leave a like and consider subscribing to the channel. There's more videos on automatic differentiation rules here, or automatic differentiation in general. Here you will now see similar videos, and I hope to see you in one of the next videos.